Hi, hello. This is Lina. Welcome to Linvis. I hope you guys are doing well. In today's video, we are going to dive into valence bond theory of coordination compounds. Okay, this is a topic from grade 12, all boards, right? Yes. And if from using this theory, you will get the complete information about the hybridization, geometry, high spin, yellow spin, diamagnetic or paramagnetic, or whether it is inner orbital complex or outer orbital complex. Okay, so complete information will be given by this theory. Okay, so make sure you stay till the end of your video. You will get some amazing tips and tricks that you don't want to miss. Also, please make sure to hit that subscribe button and ring the bell icon so you will never miss an update from us. Okay, let's now get started. So we are going to discuss about valence bond theory, as I told you. So first of all, we have to discuss the main points or salient features of valence bond theory. And we know coordination compound. Coordination compound is a compound that is made up of a central metal ion, okay, mainly transition elements, transition metals, and it is surrounded by ligands, right? Okay, so what will the central metal ion do? The central metal ion should make empty available orbitals, okay, that is equal to the coordination number of that. Okay, so these empty orbitals will undergo hybridization. Okay, and after that, what will they form? They will form equivalent hybridized orbitals. Equivalent hybridized orbitals. Okay. And these hybridized orbitals and the ligand orbitals will overlap. And we know that ligand is coming with extra electron, right? That is able to donate its electron pairs. So they will overlap and form what? Metal ligand coordinate bond. So these are the major features of valence bond theory. Okay, now we will move on to some octahedral and tetrahedral complexes, and we will discuss its hybridization, its geometry, etc. Okay, the first complex we are going to take, the simple one we will start with CONH3 6 3 plus. Okay, so to finding these valence bond theories, it's just I will give you some trick, right? First of all, you have to find the oxidation state of central metal. That is the first task. Okay, this is the first task of yours. Central metal ions oxidation state you have to find. After that, you have to go through the ligands, and you have to search whether the ligand is a strong field ligand, yeah, weak. Strong field, yeah, weak. Strong, yeah, weak. Ligand. If the ligand is strong, what will happen? Whenever there is strong person coming, what will automatically do? We have to replace them, right? We have to take our place to them. Like that, whenever there is strong ligands come, the cobalt, that means the metal here, has to give place to that ligands. Okay, so there will happen pairing. Okay, if the weak ligands are coming, what will happen? There is no pairing takes place. Okay, this is the thing you have to remember before going through the questions of the complexes. Okay, so what is first? You have to do the oxidation state of the central metal ion and check whether the ligand is strong field ligand or weak field ligand. The ligand is strong field, what will happen? Automatically pairing will take place. Okay, and if it is weak ligand, there is no pairing. Okay, now let us move on to the cobalt complex. And what is the name of this complex? 6 ammonia, right? So hexamine cobalt and ammonia NH3 is a neutral ligand, no charge. So cobalt is automatically what? Cobalt is 3 plus. Okay, cobalt is 3 plus. So you understand what the oxidation state of this metal. Cobalt 3 plus. And what is atomic number of cobalt? 27, right? Atomic number is 27. That is 3d7-4s2. Okay. If it is cobalt 3 plus, that means what? It is 3d6. Okay, that much you have to understand. And 4s, there is nothing in 4s here. Okay. And 4p is also there is nothing. We know that. Okay. Then what is happening? Let us see outer we have to draw this. Okay. In the ground state. 6, 5. 1, 2, 3, 4, 5, 6. Okay, and there was nothing here. Yeah, here it was. First, I will draw this to make you understand. 1, 2, 3, 4. Here 1, 2, 3, 4, 5, 6, 7, and in the yes there was 2. Okay, 3d7, 4s2. Okay, now what is happening? Yes, S has removed and one electron from here is also gone. Okay, yes, there is nothing in 4s and there is nothing in 4p also. Now who is coming? Yes, so we have to understand who is coming. Yes, ammonia is coming. Ammonia is a what type of ligand? Yes, it is a strong ligand. Strong ligand. So what will happen? 6 ammonia is coming, right? 6 ammonia is coming. 6 vacant orbitals should be there. So what will be the under the influence of the strong ammonia ligand, electrons in this 3D are forced to pair up. Okay, so what will happen if the electrons in the 3D are forced to pair up? What will happen? It was 1, 2 already here. Then these 4 will be paired up like this and make 2 orbitals available in 3D. And S is free here and P is there. So there are how many orbitals? 1, 2, 3, 4, 5, 6. 6 empty orbitals. That is the coordination number, right? This is the coordination number. 6 is the coordination number of this complex, right? So it has to make 6 empty orbitals. So now 6 empty orbitals are there. Then this will undergo what? Hybridization. Okay, this will undergo hybridization. These 6 orbitals, and you will be getting 1, 2, 3, 4, 5, 6 hybridized orbitals. Okay, and this is D, this is D, this is S, P, P, P. So we'll be getting D2sp3. Okay, and ammonia molecules will come and sit here with the electron pairs. So thus forms the compound, coordination compound, complex CONH3 3 plus. Okay, and so we get the hybridization. Okay, when you get the hybridization, and what is the geometry? There are 6. This is octahedral geometry, right? Octahedral. Okay, and is there any unpaired electrons? Can you see any unpaired electrons here, here and here? No, there is no unpaired electrons. That means these are diamagnetic. And in the formation of this complex, we have used inner d orbitals, right? Inner 3D orbitals we have, it is involved in this. Okay, so it will be inner orbital complex. Inner orbital complex. Okay, and it is low spin, right? Here it is forced to spin up, right? So it is low spin complex. Okay, all this information you will be getting. 5 different information you are getting. So question will be sure to find out the hybridization, magnetic property, geometry, inner, outer, everything. Okay, so if you know the concept, it is very easy to find out. Let us move on to one more this type of octahedral complex. FeCN6 3 minus. Okay, so what will happen here? Ion. So ion is 26, right? 26, atomic number 26. So 3d6, 4s2 is the electron configuration. And here cyanide is -1 charge. So ion's oxidation state is here is Fp3 plus. That means it is 3d5. Okay, 3d5, 4s0, 4p0, like that you can write. And how will you draw this? You can draw this like 1, 2, 3, 4, 5. That is 1, 2, 3, 4, 5, and 6 here. And the yes, there is 2. Okay, in the P, there is nothing. Okay, P. 3D, 4S, 4P. Okay. And this is the oxidation state of Fe3 plus. So how will you draw that? You can draw like 1, 2, 3, 4, 5. 4s there is nothing, and 4p there is nothing. Here 1 electrons in each orbital. Okay, so this is Fe3 plus ions. Okay, Fe3 plus ions. Then what is happening? Who is coming? Cn, right? Next task is to find out who is coming. Which ligand is coming? Cyanide, Cn minus. What type of ligand is that? Yes, it is a strong ligand. Very good, strong ligand. So these electron pairs are forced to pair up, right? So what will happen? So what will happen is that, yeah, you can see here they are forced to pair up. So here it will become 1, 2, 3, 4, and here there is only 1. Okay, now because there is nothing to pair up. Okay, then 2 orbitals are free now. Here 1 orbital, here 3 orbitals. Correct. 6 is the coordination number. 6 empty orbitals. And they will undergo hybridization, right? Hybridization to form what? Yes, 1, 2, 3, 4, 5, 6. Okay. And here who will come in? Cyanide will come and sit here. Okay. And here you have to mark this, and only you can find the hybridization. Okay. 1, 2, 3, 4, 5. This one. Okay. Yes. Formation of this complex is formed. And you can see here DDSPPP. Okay. That means D2sp3. Again, D2sp3 is the what? Hybridization. And yes, 6 orbitals are used, right? So this is what? Octahedral geometry. Okay. And it is very clear that there is one unpaired electron. So this is of course paramagnetic. Okay, presence of one unpaired electrons. So this is paramagnetic. So all the information you get, right? Magnetic properties, geometry, and hybridization, right? So this is how we are dealing with these type of questions. Hope you get it. Okay. Then we will do one weak ligand case. So COF6 3 minus. So here fluorine is a weak ligand. First of all, you understand the oxidation state of cobalt is 3 plus. That is 3D6. 4S0. Okay. So here 1, 2, 3, 4, 5. Okay. 1, 2, 3, 4, 5. Here 6. Okay. There is nothing in S. 4S. Okay. And 4P is here. Then what is happening here? In this case, the fluorine is coming. Fluorine F minus is a weak ligand. Weak. Okay. Weak ligand. So what will happen, guys? There is no pairing takes place. So how many fluorine atoms are coming? 6 fluorine atoms, right? There is only 4 here. We have to take the outer d orbitals. Okay, 4 d orbitals we have to take. Okay, then these 6 orbitals will undergo hybridization. Okay, so you will be getting what? Fluorine F minus can come and accommodate in these orbitals, and you will be getting this is S, P, 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 and this is D, D. So what is the hybridization? sp3d2 is the hybridization. Okay, here you can see here 1, 2 inner d orbitals are not at all participated here. Okay, so here you can see 4 unpaired electrons. Okay, 4 unpaired electrons are there. That means it is very paramagnetic. And also you can see here the hybridization is sp3. So what is its geometry? Yes, it is of course octahedral geometry. Okay. And what type of complex is that? Outer D is used, right? So this is outer orbital complex. Okay. And it is high spin complex, right? High spin. So this is the method we are doing. Okay. Hope you get it. Okay. Next we will do some tetrahedral complexes 1 or 2. Okay. Very simple. Nickel Cl4 2 minus. Here nickel is in +2 oxidation state. So that is 3D8. Okay. Then just draw this 3D8. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8. There is no S, there is no P electrons. Okay. 3D8 is the configuration of Ni2+. Okay. Yes. Now you can do it directly, no need of finding nickel, then nickel 2 plus. So after practicing, you will be getting thorough. Okay. Yes. Then what is happening? Cl minus. Cl minus is a weak ligand. Fluorine, chlorine, bromine, they are all weak ligands. Okay. So there is no pairing up takes place. And the 4 is the coordination number. Yes, there are 4 orbitals here, right? So what will be the hybridization here? SPPP, right? So this is sp3 hybridization. Whenever you see sp3 hybridization, yes, it is tetrahedral geometry. Okay. And what about this magnetic properties? Para, there is unpaired electrons. Paramagnetic. And what is its spin? Yes, it is high spin complex. High spin. Yes, moving to the next one. That is, let us do another example of nickel complex. Nickel CN4 2 minus. Here, same, nickel is in what? Plus 2 oxidation state, right? 2 plus oxidation state, that is 3D8. But what is here? Cyanide, Cn minus. That is a strong ligand. Strong ligand. So what you have to do? You have to pair it up. Okay, that is the thing you have to keep in your mind. So 3D8, right? It was 3D8. 1, 2, 3, 4, 5, 6, 7, 8. It is forced to pair up means what? It will become like 1, 2, 3, 4, 5, 6, 7, 8. One vacant orbital here. And here S is there. Here P is also there. Okay. 3D8. 4S. 4p is there. We have to make 4 orbitals, right? 4 orbitals means you have to take, definitely we have to take this d orbitals, okay? And 1s and 2p we have to take, okay? No need of 3p, okay? So these are the hybridization, undergoing hybridization. Okay, 1d, yes, pp. So that means what is hybridization of this? DSP2 is the hybridization. Whenever you see DSP2 hybridization, yes, this is square planar complex. This is a square planar complex. There is no unpaired electron, so this is what? Yes, this is the diamagnetic. And here inner d orbitals are used. So inner orbital complex. It is inner orbital complex. Okay. Yes. So this is all about what? Hybridization, then geometry, etc. Okay. While using Valence Bond theory, we will get a clear-cut information. And inner orbitals, what do you mean by inner and outer orbital complex? Inner orbital complex means what? It is found by using inner d orbital, that is n minus 1 d orbitals. Okay. That is, in the formation of inner d orbitals, electrons in the metal ion are forced to pair up. Okay. So such a complex will have either no unpaired electron or will have few unpaired electrons. And this is a low spin complex. Low spin. Okay. Always low spin. Or we call it as it is forced to pair up, right? Inner d orbitals are forced to pair up. So this is spin paired complex. What about outer d orbitals? Outer orbital complex. What is that? Outer orbital complex. We are using what? Nd orbitals. Nd. Nd means outer d orbitals we are using. For example, sp3d2. Okay, example. And here there will be lot of unpaired electrons. Okay. Yes, it has a chance. And it is a high spin complex. It is high spin. Or it is also called as spin free. Spin. This is here spin is pairing takes place, right? Because of the strong ligand count. Here spin is free. So it is called as spin free complex. And let us understand the limitations of valence bond theory. Limitations also you have to understand. Limitation. So magnetic properties of these coordination compounds are explained only qualitatively. We are not calculating the magnetic moment here, right? So quantitatively, we are not able to find out what the magnetic properties. Magnetic properties here only what? Qualitatively. That is one of the limitations, okay? And this VBT, that is valence bond theory, fails to account what? Fails to account the color of the complex. Color of complex. Okay. Next is, it does not give an explanation about fails to tell about what? Stability. Okay. So these are the major limitations of what? Valence bond theory. Okay. So hope you have watched the video very carefully. Hope you understand the video. If you enjoyed this video and found it helpful, don't forget to give a thumbs up and please share it with your friends. Okay, leave a comment below if you have any questions or suggestions for the future videos. I would like to hear from you, and if you have already, make sure you have subscribed our channel. Okay, and please click the bell icon so you will never miss an update from us. So stay curious, keep learning. We will see you in the next video. Bye for now. Thank you.